Jai Hind to all. I'm Divya Sharma. Now today's lecture on continuity equation, relaxation time and boundary conditions. So first we will cover this topic, continuity equation. Now due to principal charge conservation, the time rate of decrease of charge within a given volume must be equal to net outward current flow. So if we are considering a case of closed surface of volume, then current out is equal to what? Closed integration J dot ds, and that is equal to what? Already we have done in the previous lecture, that is equal to minus d upon dt q in. So now q in is the total charge enclosed by the surface. Here you can apply, here you have to apply the divergence theorem, and you all know divergence theorem is what? Closed integral surface J dot ds is equal to closed integral delta dot j dv. So this is divergence theorem. So you can apply here divergence theorem, and here that is equal, here I out is equal to minus dqn upon dt. So put here the value of qn. So minus d upon dt, q in is equal to integration del v dv. Now here that is equal to minus integration del your density rho v upon dt and dv. Now substituting, this is equation B and this is equation C. When you are substituting these two equations in this equation A, so you will get here integration del dot j dv is equal to minus integration del rho v upon delta t into dv. So here from this equation you will get, this is in form of volume, integration form of volume, here is also. So you can write down it, del dot j is equal to minus del rho v upon del t. So this is the continuity of current equation. Now next is relaxation time. Relaxation time, now continuity equation and its properties rho and epsilon of materials. Now consider the effect of introducing charge at some interior part of the given material, and given material, let it be that may be conductor or dielectric. Now here we make use of equation D as we have done the previous equation. This is the D equation. Now here in conjunction with Ohm's law, J is equal to rho v. As you all know, what do you mean by Ohm's law? So, and Gauss law is equal to what? Del dot E rho is equal to rho v upon epsilon. Now substitute this equation and this equation in equation D. Then you will get delta dot rho v, rho E, sorry, this is rho E is equal to rho v, sorry, delta dot sigma E is equal to sigma rho v upon epsilon, and that is equal to what? That is equal to minus del rho v upon delta t. When you are substituting this equation in the previous D equation, you will get this relation. Now here when you will get this relation, you can rearrange this equation and you will get here del rho v upon del t. You can take this here in left hand side, so minus your, you can say del rho v upon del t plus sigma upon epsilon rho v is equal to 0. So this is the final equation. When you will put this equation and this equation in the previous equation, you will get this relation in between rho v and rho v, sigma and epsilon. Now this is the homogeneous linear ordinary differential equation. When you are separating these variables, then you will get equation del rho v upon rho v is equal to minus sigma upon epsilon del t. So this is the relation for relaxation time. Now here when you are integrating these two parts, then you will get ln rho v is equal to minus sigma t upon epsilon plus ln rho v naught. Now rho v is what? This is constant of integration. When you are integrating this, then you will get this rho v is equal to rho v naught E minus sigma or minus t upon tr. Now tr is what? Epsilon upon sigma. Or you can say, you can write it like this, ln rho v upon ln, or you can say ln rho v minus ln rho v naught is equal to minus sigma t upon epsilon, or you can say ln rho v naught minus ln rho v is equal to sigma t upon epsilon, ln rho v naught upon rho v is equal to sigma t upon epsilon. So if you want to find out rho v, so rho v is equal to rho v naught e की power minus t upon tr. If your tr is equal to what? Tr is equal to epsilon upon sigma. So you will get relation rho v is equal to rho v naught e की power minus t upon tr, and tr is what? Tr is the relaxation time. Rho v naught is the initial charge density, and rho v at t is equal to 0. You have to find out this relation. Now this is the equation as we are introducing charge at some interior point of the material, or you can say there is a decay of volume charge density rho v. Now tr is the relaxation time, that is in seconds, or you can say this is the rearrangement of time. Now relaxation time is the time it takes you charge placed in the interior of the material to drop to E, and 1 upon E is equal to what? 36.8% of the initial value, and it is short for good conductors and is long for, means relaxation time is short for good conductors and long for good dielectrics. Now the boundary conditions. Now we have to consider the existence of electric field in a homogeneous medium. Now if a field exists in a region consists of two media, now conditions for that field, if we are separating that media, means you have to apply some boundary conditions over the setup of when you have two points or there is a media in between that 2 points, that is known as you have to set the boundary conditions. Now these boundary conditions are helpful in determining the field on one side of the boundary if the other side of the boundary side is known. Okay. Now we shall consider the boundary condition at an interface separating when you have dielectric, that is denoted by epsilon r1, and other dielectric, that is representing by epsilon r2. Now the second is conductor for conductor and dielectric, and conductor for free space. Now here to determine the boundary conditions, we need to use Maxwell equation, means you should know the Maxwell equation, then only you can find out the boundary conditions. Now closed integral E dot dl is equal to 0, and here closed integral D dot ds is equal to Q enclosed, as we have done this equation previously, and this is also done, and we have to use here Maxwell equation. Now here we need to decompose electric field intensity E in two orthogonal components, that is E is equal to ET plus EN. Now what do you mean by ET? ET is the tangential component of E, and EN is the normal component of E, that is used to interface of means interest, means ET and EN stands for tangential and normal components of E. Now here a similar decomposition can be done for the electric flux density, that is represented by D, that is equal to what? Now first we have to cover dielectric boundary conditions. Let it be, this is your E2N, this is your E2, and this is when you are covering this point to this point, that is denoted by E21. Now here let it be, this is E1, this is E1N, and when you are covering this distance, that is denoted by E11, and let it be you have a rectangle here surface, or you can considering a surface A, B, C, D. So here this is surface distance is denoted by delta W, and this height of this surface is delta H. Now here E2 is the dielectric constant. Now here consider a field E existing in a region consists of two different dielectrics. Two different dielectrics are represented by epsilon 1 and epsilon 2. Now epsilon 1 is equal to what? Epsilon 1 is equal to epsilon naught. Epsilon R1 and epsilon 2 is equal to what? Epsilon 2 is equal to epsilon naught epsilon R2. Now here E1 and E2 are in media 1 and media 2. So it can be decomposed into two parts. E1 is equal to E1t plus En. This is your tangential part and this is your normal part for this E1 media. Now E2 is equal to E2t plus E2n, means this is your tangential part and this is the normal part. Now here we have to apply equation 1a to the closed path. You have a closed surface A, B, C, D, A. In this figure A, assuming that the path is very small with respect to the variation of E. Now E1t is equal to E2t. Now this is also, let it be, this is an equation. Now tangential components of E are the same on the two sides of the boundary. Now or you can say E undergoes no change on the boundary and it is said to be continuous across the boundary. Now D is equal to what? D is equal to epsilon E, and if you are decomposing into two components, that is in form of tangential and normal, so that is equal to what? dt plus dn. Now you can write down it like this: d1t upon epsilon 1, that is equal to E1t. E1t and E2t are common, means equal to each other. So you can write down d1t upon epsilon 1, that is equal to d21 upon epsilon 2. Now T undergoes some change across the interface. Now D is also called discontinuous across the interface. Now as you all know, according to the Gaussian surface, if you are aligned, delta H tends to 0. So delta Q is equal to rho delta S. Delta is your surface and rho S is the charge density of the surface, and Q is the charge on that surface, that is denoted by delta S. Now if you are decomposing, if you are write downing charge density, rho S is equal to what? Rho S is equal to D1n minus Dn2. Now here rho S is equal to D1n minus D2n, sorry, and you can put the value of charge density here. You will get here delta Q is equal to what? Rho S delta S. Now rho S is equal to what? Rho S is equal to D1n minus D2n. So put this value of rho S, then you will get here D1n delta S minus D2n delta S. So rho S is the first free charge density placed at the boundary. Now if no free charges existing at the interface, then charges are not deliberately placed there. It means what? Rho S is equal to 0. If rho S is equal to 0 here, it means D1n is equal to D2n. So from this equation, if you will put here rho S is equal to 0, so D1n is equal to D2n. Now normal component of D is continuous across the interface. It means Dn undergoes no change at the boundary. If no change at the boundary, since D is equal to epsilon E. In the previous equation, D is equal to epsilon E. If you are comparing D1 and D2, then you can write down epsilon 1 E1n is equal to epsilon 2 E2n. It means what? It means it's showing the normal component of E is discontinuous at the boundary. Okay. Now we can use boundary conditions to determine the refraction of electric field at the interface, and considering D1 or E1, D2 or E2 making angles theta 1 and theta 2 with the normal to the interface. Let it be, this is the interface, this is the origin, and here you can see this is the D2 and this is D2n. An angle between in this D2 and D2n angle is theta 2. And let it be, you have another surface from this origin. This is your covering distance E1. Here is the electric field E1. And here you have E11, and joining this distance, that is denoted by D1n. This is D1n. Now here angle in between means this is, let it be, this is your axis, so, and this is the distance, so angle between in this is theta r. So here you are considering you have to consider two boundary conditions for theta 1 and theta 2. Theta 1 is here and theta 2 is this one. So now here E1 sin theta 1, it means what? E1t is equal to E2t. So put the value here E1t. E1t you can find out from this figure. E1t here, E1t is equal into sin theta 1. From this figure you can find out E1 sin theta 1, and from this figure you can find out E2n, and E2t is equal to what? E2 sin theta 2. Or you can write down E1 sin theta 1 is equal to E2 sin theta 2. And by applying equation P and Q, you will get here epsilon 1 E1 cos theta 1 is equal to D1n is equal to D2n. So you can write down the value of D1n is equal to what? Epsilon 1 E1 cos theta 1 and epsilon 2 E2 cos theta 2. Now divide this equation R, this is equation R, divided by this equation S, then you will get here tan theta 1 upon epsilon 1 is equal to tan theta 2 upon epsilon 2. And epsilon 1, you all know epsilon 1 is equal to epsilon naught, epsilon R1, epsilon 2 is equal to what? Epsilon naught, epsilon R2. So you can put these values here and you will get the final equation, that is tan theta 1 upon tan theta 2 is equal to epsilon R1 upon epsilon R2. So this is the law of refraction of electric field at the boundary of free charge since rho s is equal to 0. Now the second condition, second boundary condition for conductor dielectric boundary condition. Let it be you have a conductor E is equal to 0 here and you have a conductor E is equal to 0 here. Now this is your dielectric. So this is En at the y-axis and x-axis Et. So its average, or you can find out the resultant of En and Et is equal to E. Let it be you are considering this surface A, B, C, D. Now here this distance is delta W and this height is delta H. So, and you all know epsilon is equal to epsilon naught, epsilon R. Now here you are considering this is a cylindrical part. This is your rectangular conductor and this is your cylindrical part. Now height of this surface is delta H and surface is denoted by delta S. Here is also epsilon is equal to epsilon naught R. Epsilon R. Now conductor is assumed to be perfect. It means what? Sigma is equal to 0 and rho C is equal to 0. Now although such a conductor is not a practically realizable, we may regard conductors such as copper or silver. Now they were perfect conductors, but here you have to determine boundary conditions for conductor dielectric interface. Now here this procedure is also same as you have done for the dielectric and dielectric interface, except E is equal to 0 inside the conductor. So here we get Et is equal to 0 and Dn is equal to rho s. Now you should remember these 3 points, that no electric field may exist within a conductor means rho v is equal to 0 and E is equal to 0. And since E is equal to minus del V is equal to 0, it means no potential difference between any 2 points in the conductor. It means conductor is a equipotential body. Now electric field can be external to the conductor and normal to its surface. It means what? dt is equal to 0 and dn is equal to rho s. Now important application for this fact is E is equal to 0 inside a conductor or in electrostatic screening or shielding. Now thank you for this lecture.